Hello, everyone, and welcome to Toronto Machine Learning Summit on NLP, and of course, welcome to this talk. Today, we have Patricia for this talk, and before I pass it over to Patricia, let's maybe if you don't know her, let's get to know her better. Patricia is the co-founder and CEO of Private AI, a Toronto and Berlin-based startup, creating a suite of privacy tools that make it easy to comply with data protection regulations, mitigate cybersecurity threats, and maintain customer trust. She is a computer science PhD candidate at the University of Toronto and a postgraduate affiliate at the Vector Institute, doing research on privacy-preserving natural language processing with a focus on applied cryptography. Her research interests also include computational methods for lost language decipherment. She has 9 years of research and software development experience, including at the McGill Language Development Lab, the University of Toronto's Computational Linguistics Lab, the University of Toronto's Department of Linguistics, and the Public Health Agency of Canada. She is also a member of the board of directors of Equity Showcase, one of Canada's oldest non-for-profit charitable organization. I'm really excited for this one. And before I pass it over to Patricia, please feel free to post your questions in the chat section, and we'll make sure to discuss your question at the end of the talk. So without further ado, back to you, Patricia.
Thank you so much for the introduction, Bita. It's great to be here. Thank you, everyone, for attending. I'm really excited about talking about the latest advances in privacy-preserving NLP. This is the thing I like talking about the most. So please ask as many questions as you want at the end. First of all, I want to start by talking about what the 4 pillars are of privacy-preserving AI. First, there's training data privacy. That's really making sure that you can't reconstruct the sensitive information within the training data, for example. Input data privacy and output data privacy, that's really about the privacy of the individual whose data you're inferring upon. Model weights privacy is about the privacy of the model of a particular corporation or a particular institution, individual who created it. So the IP protection there. And the output privacy also can fit in there because you can determine information about the model from the output, but that's a little bit nuanced. A lot of the R&D focuses on training data privacy, and that's what we'll be focusing on today. One piece of research that was a pinnacle piece for understanding training data privacy in NLP is Carlini et al.'s The Secret Share, Evaluating and Testing Unintended Memorization in Neural Networks. And if you've heard talks about privacy-preserving NLP in the past, you've probably heard this paper mentioned. So I'll briefly just mention what their work is. They put a canary, this number, into the patent tree bank data set, and then trained a character language model on it. LSTM was one of them, and then a few others, and measured the perplexity of that language model when it came to predicting that number, as well as other numbers with similar prompts. And it turned out that the perplexity, so the amount of surprise that the model has at seeing a particular output, was lower for that number over any other number that was similar to it. And what that means is that the model memorized the secret. And that's a problem because we are training language models for all sorts of tasks, and we might not always be thinking about what the privacy of the training data itself. The Carlini et al. Then in 2020 came out with this paper, Extracting Training Data from Large Language Models, and showed that GPT-2 was actually memorizing sensitive data from the pre-training data that it was trained on. So it was outputting full addresses, names, and yes, this data is out in the public, so there is no ethical dilemma there of really showing the sensitive data that GPT-2 is producing. But it's important to keep in mind that once those models are pre-trained, they're then trained on internal data sets, which could be healthcare data sets or other. And it's pretty clear that from a few examples, so in the case of GPT-2, for a extra large model, with 33 examples, it already started memorizing the sensitive data. There's also this really great work by Mohammed Abdallah et al. From the University of Toronto, exploring the privacy-preserving properties of word embeddings, an algorithmic validation study. And this is studying the privacy of word embeddings when they're trained on the mimic data set. So what Abdallah did is took away 99% of the names that were, of course, pseudonyms. They weren't actual names of the patients within the mimic data set, which is a healthcare data set, and kept 1%. So assuming that you just used redaction, but a really not great redaction that didn't capture all of the names of the patients. And then assume that the patients that were mentioned, so of the word embeddings that were created, had the names of the patients that were mentioned. Because usually after you train the word embeddings, make them public, you then have a list of all of the names and all of the words that are associated with each embedding. And he showed that if you calculated the distance between the word embeddings for the first name and last name of a particular individuals, it was shorter if they were actually corresponding first name, last name, than the distance between the first name and last name of different individuals. And that was particularly interesting because that shows that you could have a membership inference attack, if you just publish word embeddings that are trained on poorly redacted data. And then the second experiment they did, which is shown on this table 3, is to comparing the distance between the names found and the diagnostic codes for each of the patients. And it was shown that GLOVE in particular is particularly bad at maintaining the privacy of the individuals when trained on the mimic data set, and with that 1% of the names that were maintained. Because for 70% of the names that were mentioned, there was a statistically significant calculation that you could make for making sure that the distance between that name and the diagnostic code was small enough to associate one to the other. And the shorter the window, usually the less likely it is that you could associate the name with a particular diagnostic code. Something to think about, but definitely something to be aware of when you are making your algorithms or your embeddings public. So there are a few privacy concerns to think about. There's identity disclosure, so identifying an individual. There's attribute disclosure, identifying what their ethnicity is, what religion, what physical attributes they have, things like that. Group attribute disclosure, so is a particular group more likely to have cancer, for example. Membership disclosure, for example, is this person part of a specific group. And not all attributes are the same. So there are direct identifiers which identify an individual directly, like a name, depending on the data set you have, a social security number, an exact address, and then quasi-identifiers like approximate addresses, physical attributes, anything where combined together, it increases exponentially the likelihood of re-identifying an individual. And context is really important when you're trying to understand what the effects of each of these identifiers are. Even direct identifiers like a social security number, if you don't have the name of the individual, you might not be able to associate it directly with the individual unless you have the right data set. A credit card number, for example, you could just make one up and that would be a direct identifier if you have the right data set. But if you don't have the associated name with a credit card number, that's not going to do you much good. So context is really key. In the wild, you'll see, for example, cases of identity and attribute disclosure. This is a South Korean love bot, which was spewing out names, nicknames, home addresses, and the responses that it was giving to its users. And it even boasted about the large data set of 10 billion intimate conversation logs. And what the problem here is that you could then infer which people were part of the user base of this Korean love bot. And that's membership disclosure through identity disclosure. That's the major problem here. There are a lot of sources of personal data when you're dealing with NLP. You could be dealing with call transcripts, with customer service emails, support tickets, you name it. There's just some of the most sensitive information we produce is through the language that we communicate in. So clearly there's going to be quite a bit of scope to cover. One solution is using differential privacy. That was used in Carlini et al.'s paper, The Secret Share, for example, specifically differentially private gradient descent. So the initial idea behind differential privacy, if you're not aware, is you're supposed to be able to make generalizations about a population, but not memorize specific information about an individual, or not be able to determine specific information about an individual. So if you had a data set and you were querying that data set for how many people have cancer and smoke, you'll get a fairly large number, and then adding a little bit of noise that won't affect your conclusions. However, if you asked how many people have cancer, have this other rare disease, and smoke, if you were to get an exact number, you could then infer who is part of that data set. However, if you have this differentially private noise that's added to it, it's difficult to tell whether if you get a 1, for example, whether it was actually 1 or 2 people or no people who are part of that data set. Just to give you a bit of an idea there. And then this notion was transferred over to the machine learning realm, and the idea is that you have this random algorithm where if you were to defer a data set by just one entry and run the same algorithm on that data set, it's just as likely for you to have the same result from that algorithm running on that data set. So you're not going to be able to infer anything about, in this case, an individual S, for example, or a particular text message S, for example. And usually this is done through gradient clipping, so limiting your gradient to a particular radius and adding differentially private noise to the direction of the gradient. Before I get to the other one issue with differential privacy is that while it does provide mathematical guarantees of worst case scenarios, there are several papers that studied its effects on underrepresented groups, and how, because there's little data on underrepresented groups, if you prevent the model from memorizing too much from small samples, then you're not going to have machine learning models that work well for these groups, and that can be quite problematic. Another problem is that you can't look at the data itself, right? And that's really useful for debugging the machine learning systems you're working on. So another solution is good redaction or de-identification, and that's removing the identifiers and quasi-identifiers within the data that you're dealing with. And in this case, for example, you remove policy number, location, date, name, phone number, and you can still tell a lot about what's happening here. You could use this to train a customer service representative, talk about what exactly happened. The vehicle was parked at a particular location, a truck hit my car from behind, the back of my car got smashed, then talk about what claim size that particular individual is eligible for, right? Or you could use this to determine how what the sentiment is of a conversation, what kind of product somebody wanted to buy, whether a particular customer service agent needs training. There's a lot of information that you can gather from natural language that really the private data is making it toxic and it's superfluous to the task. The one issue with something like that, however, is that if you are training your machine learning models with this information, your NLP models are generally pre-trained on a huge amount of data that does not look like this. So you want your training data to be as similar as possible to your pre-training data, so for it to get the highest accuracy possible for your tasks. So another option is targeted synthetic data generation. And this is just making things very natural. It has an additional benefit of making it more difficult, if anything is missed, to determine what the real information is from the incorrect information. So we tested out the reduction versus targeted synthetic data generation in various NLP tasks, including sentiment analysis, named entity recognition. And this is something we're working on publishing, but we've noticed that it really does prevent downstream model accuracy loss, which is super cool in a privacy preserving way, right? And it also reduces the re-identification risk. If you look at the paper by Abdallah 2020, they mentioned this as part of the study for word embeddings that I mentioned. That's it. Happy to take any of your questions. And we do have a privacy enhancing technologies decision tree on our website if ever you're curious about which privacy enhancing technology is right for you.
Thank you, Patricia, for the great presentation. I think in the industry, we all face this challenge of how to preserve the data of, no matter if it's a public industry or any other industry that we work with personal data to make sure that we preserve the privacy of our participant in our data set. So that's great. I'm just looking at the chat section. Please feel free to ask any questions that you might have. So Patricia here can answer your questions. And I see that we have also your Medium channel here. So our participants, if they want to learn more in details about what you've discussed today, they can also check out your Medium and to read your articles to become more familiar with the work that you've done.
And if anyone ever has any questions, feel free to email me. Happy to talk.
Thank you. Thank you so much. And it seems that right now we don't have any questions, but I'm sure that can we have your email? You've mentioned that if there is any questions. So our participant, okay, great. Thank you. Thank you so much. It was a great talk, and thank you for being here with us.
Thank you very much.
And thank you. And thank you all for listening.